sapbric of gravity is the weakest force in the universe. Not moderately weak, not slightly underpowered. Weaker than electromagnetism by a factor of 10 to the power of 36. That is a 1 followed by 36 zeros. And yet, it is the only force that governs everything you can see across the entire observable universe. Every galaxy, every star, every orbit, every collision between worlds. Richard Feynman, Nobel laureate, the man widely regarded as the greatest physics communicator who ever lived, said something about this that most people have never heard. Something that, once you understand it, permanently changes how you think about the possibility of alien civilizations, he said. If an advanced civilization existed with the technology to cross interstellar space and visit Earth, the physics of gravity itself would make that civilization visible to us. Detectable, unavoidable, and we see nothing. That silence, Feynman argued, is not an absence of data. It is data. Here is what most people believe about the Fermi paradox, the question of why we haven't detected alien civilizations. They believe the silence means aliens are hiding, that they are watching us from a careful distance, that they have made a deliberate choice called the zoo hypothesis to observe humanity without interfering, the way a scientist watches bacteria in a petri dish. It is a comforting idea. It makes humans feel observed, special, protected even. But here is the problem with that theory. It assumes that an advanced civilization, one capable of crossing the 4 light years between us and the nearest star system, Alpha Centauri, could do so without leaving a thermodynamic signature that we would be physically incapable of missing. And this is where the physics of gravity destroys that assumption entirely. The zoo hypothesis doesn't fail because of philosophy. It doesn't fail because of biology or sociology. It fails because of the second law of thermodynamics and because of what? Gravity requires any sufficiently advanced civilization to do with energy. So the real question isn't, are aliens hiding from us? The real question is, could they hide from us even if they wanted to? What I'm about to show you sits at the intersection of 3 fields: gravitational physics, thermodynamics, and information theory. In 1959, physicist Philip Morrison and Giuseppe Cocconi at Cornell University published the first serious scientific paper on the detectability of extraterrestrial civilizations, not through UFO sightings, but through physics, through what the laws of nature require any energy-using civilization to produce. That paper launched the field of SETI, the search for extraterrestrial intelligence. But Feynman's contribution was different, more fundamental. He asked a question nobody else was asking at the time. Not, where are they? But, what does gravity tell us about what they would have to do, and why we would inevitably see it? The answer runs through one of the most misunderstood forces in all of physics. And by the end of this video, you will understand exactly why the universe's weakest force is also its most powerful cosmological fingerprint. Let's start at the foundation. Gravity, in Newtonian terms, is a force between any 2 objects with mass. The formula is precise. F equals g times m1 times m2, divided by the square of the distance between them. G is the gravitational constant, negative 6.674 times 10 to the negative 11 cubic meters per kilogram per second squared. That number G is extraordinarily small. It is the reason you can pick up a coffee cup with the muscles in your fingers, overcoming the gravitational attraction of the entire planet Earth with a few ounces of force. Think about that. The electromagnetic force binding your muscle fibers together is stronger than the gravity of a 6 septillion kilogram planet. Now, in Einstein's reformulation General Relativity, published in 1915, gravity is not a force at all. Mass tells space-time how to curve. Space-time tells mass how to move. And the consequence of that curvature is what we experience as gravitational attraction. This is not a metaphor. It is the most precisely tested theory in the history of science. GPS satellites require relativistic gravitational corrections of 45 microseconds per day to function accurately. Without those corrections, your GPS would drift by 10 kilometers per day. Gravity is not just a force that pulls things together. It is an energy cost, a tax. an unavoidable thermodynamic expense that every civilization in the universe must pay. To move anything, a spacecraft, a probe, a signal away from a gravitational source, you must do work against that gravitational field. You must expend energy. And the amount of energy required scales with the mass of what you're moving and the depth of the gravitational well you're climbing out of. The escape velocity from Earth's surface is 11.2 kilometers per second. To achieve that velocity, a 1 kilogram object requires approximately 63 megajoules of energy. That is roughly equivalent to the energy stored in 15 kilograms of TNT to move 1 kilogram of mass to interstellar space. Now scale that to a spacecraft capable of carrying biological beings, life support, navigation, propulsion, and fuel across 4 light years to Alpha Centauri. The Voyager 1 probe, the farthest human-made object from Earth, was launched in 1977. It's currently 23.3 billion kilometers away. It took 46 years to travel that distance. Alpha Centauri is 4.37 light-years away, approximately 41.3 trillion kilometers. At Voyager's speed, it would take approximately 73,000 years to reach it. And this is where it gets strange. Because if an advanced civilization wanted to make that journey in a reasonable time frame, say, a few hundred years, they would need to travel at a significant fraction of the speed of light, at least 1 to 10%. SOV, and the energy required to accelerate a crude vessel to even 1% of light speed is not just large. It is cosmologically significant. Physicist Michio Kaku, drawing on the Kardashev scale, a classification system for civilizations based on energy use proposed by Soviet astronomer Nikolai Kardashev in 1964, has calculated that a civilization capable of routine interstellar travel would need to be harnessing energy at the scale of an entire star. A Kardashev Type 2 civilization. 1. That captures and uses 100% of its host star's energy output, approximately 3.8 times 10 to the power of 26 watts for a star like our Sun. That is not a hypothetical flourish. That is a thermodynamic requirement. The physics of gravity and inertia demand it. Here is where Feynman's reasoning becomes forensically precise, and where the zoo hypothesis collapses under its own physics. A civilization harnessing stellar-scale energy does not just use that energy cleanly. The second law of thermodynamics, one of the most absolute laws in all of physics, states that no energy conversion process is 100% efficient. Every time energy is converted from one form to another, some of it is lost as heat. This is not a technological limitation. It is not something a sufficiently advanced civilization can engineer around. It is written into the mathematical structure of the universe. The formal statement, developed by Rudolf Clausius in 1865, is this: the entropy of an isolated system always increases. Heat flows from hot to cold. Waste energy is an inescapable byproduct of doing work. Now apply this to a Kardashev Type 2 civilization 1, capturing the full output of a star. Even at 99% efficiency, which is thermodynamically impossible, but let's grant it as a thought. Experiment 1% of 3.8 times 10 to the 26 watts is still 3.8 times 10 to the 24 watts of waste heat. That must go somewhere. It radiates into space as infrared radiation. Here's what the data actually shows. In 2015, astronomer Tabitha Boyajian at Yale University announced the discovery of a star KIC 8462852, now called Boyajian star, that exhibited the most unusual dimming pattern ever recorded in 150,000 stars observed by the Kepler Space Telescope. The star dimmed by up to 22% at irregular intervals. No natural planetary transit produces that kind of dimming. A planet the size of Jupiter dims a star by approximately 1%. The scientific community briefly, seriously, entertained the possibility of a Dyson sphere under partial construction, a megastructure, the infrared signature of a civilization. They looked for the waste heat. They pointed the Spitzer Space Telescope and Infrared Observatory at KIC 8462852. They found nothing anomalous. The dimming was later attributed to dust, a mundane but scientifically honest answer. But the method of inquiry reveals something profound. We already know how to look for advanced civilizations, and we know exactly what to look for, because the laws of thermodynamics tell us what they cannot hide. In 2015, Penn State astronomer Jason Wright published a systematic survey using data from NASA Wide Field Infrared Survey. Explorer-wise searching for the waste heat signatures of Kardashev Type 2 and Type 3 civilizations across 100,000 galaxies. The study, titled The G-Circumflex Infrared Search for Extraterrestrial Civilizations with Large Energy Supplies, found no convincing candidates. Not one galaxy showing anomalous infrared excess consistent with galaxy-scale energy harvesting. 100,000 galaxies, each containing hundreds of billions of stars. Zero detections. But this is where it gets strange, because the absence is not just statistically significant. It is physically eloquent. Consider what it would take for an advanced civilization to hide this waste heat signature. To be invisible to an infrared survey, they would need to dissipate waste heat into a medium that does not radiate in the infrared. But there is no such medium accessible through known physics. All matter above absolute zero radiates thermally. The universe's background temperature, the cosmic microwave background, is 2.725 Kelvin. Any civilization using meaningful energy operates at temperatures far above that. The contrast is unavoidable. Alternatively, they could somehow violate the second law of thermodynamics. Build a Maxwell's demon, a hypothetical device proposed by James Clerk Maxwell in 1867 that sorts fast and slow molecules to reverse entropy. But physicist Leon Brillouin proved in 1951 that a Maxwell's demon must itself generate entropy when acquiring information. The act of measurement carries a thermodynamic cost. You cannot cheat entropy, not even with arbitrarily advanced technology. The physicist Freeman Dyson, who first formalized the concept of the stellar energy-capturing megastructure in his 1960 paper, Search for Artificial Stellar Sources of Infrared Radiation, in the journal Science, was explicit about this. He wrote that any civilization with the energy needs implied by interstellar travel would be thermodynamically loud, not detectable with sufficient technology, detectable with current technology. We are not waiting for better telescopes. We already have the instruments. We have conducted the surveys. The universe is not whispering. It is silent. Now let's ask the deeper question, the one Feynman was really pointing at. Why does gravity make this silence so significant? What is it about the specific weakness of gravity that turns the absence of detection into a positive scientific statement? Here is the mechanism. Gravity is weak at short ranges but cumulative at cosmic scales. It never cancels. Unlike electromagnetism, where positive and negative charges can neutralize each other, mass only adds. Every gram of mass contributes to the gravitational field. There is no negative mass, no gravitational shielding. This means that at the scale of galaxies and galaxy clusters, gravity is the dominant force. The large-scale structure of the universe, the cosmic web of filaments and voids mapped by the Sloan Digital Sky Survey, is entirely a gravitational sculpture. 100 billion galaxies organized by nothing but the accumulated gravity of matter over 13.8 billion years. Now here is Feynman's specific contribution to this argument, and it requires understanding something called the gravitational binding energy of a star, the gravitational binding energy of our sun, the energy required to completely disperse all the sun's mass against its own gravity is approximately 2.3 times 10 to the power of 41 joules. That number is almost incomprehensibly large. For comparison, the sun's total luminosity, its energy output per second, is 3.8 times 10 to the 26 watts. It would take the sun approximately 19 million years of continuous full power output to accumulate the energy equal to its own gravitational binding energy. Feynman's point was this: a civilization that has solved interstellar travel has necessarily solved energy generation at scales approaching stellar binding energies. Not just power generation, gravitational engineering. The ability to work with, against, or alongside gravitational fields at scales that dwarf anything in our current technological vocabulary. And here's what nobody tells you about what that implies. A civilization at that energy scale would not be invisible in the seational domain either. General relativity predicts that accelerating masses produce gravitational waves, ripples in the fabric of space-time itself. In 2015, the LIGO detector, the Laser Interferometer Gravitational Wave Observatory, detected gravitational waves for the first time, produced by two black holes merging 1.3 billion light-years away. The signal was a space-time distortion of 10 to the negative 21 meters smaller than a proton by a factor of 1,000 detected across a 4-kilometer interferometer arm. That detection came from a natural event, two black holes. A collision that produced more energy in its final milliseconds than all the stars in the observable universe combined produce in light. Now, consider. A Kardashev Type II civilization maneuvering stellar mass objects as part of its engineering infrastructure, as physicist Dan Hooper of Fermilab has theorized some civilizations might do to escape the expansion of the universe, would produce gravitational wave signatures of its own, potentially detectable signatures. LIGO and its successor, LISA, the Laser Interferometer Space Antenna. A proposed space-based gravitational wave observatory would be sensitive to these signatures. Advanced LIGO successor, the Einstein telescope, planned for construction in Europe, will be sensitive to gravitational wave sources across a volume of space approximately 1,000 times larger than current detectors. We are, in essence, building a civilization detection instrument. And the silence so far is telling. And this is where it stops being about Feynman and starts being about the question you actually came here to ask. If the laws of physics guarantee that an advanced civilization is thermodynamically visible, gravitationally detectable, and infrared loud, and if we have looked and found nothing, what does that actually mean? What Feynman was articulating, though he expressed it through physics rather than philosophy, is principle we might call the Thermodynamic Visibility Law of civilizations. State it formally. Any civilization that uses energy at the scale required for interstellar travel necessarily produces thermodynamic, electromagnetic, and gravitational signatures that exceed the detection threshold of any civilization with equivalent or greater technological capability. This is not a conjecture. It derives directly from three foundational laws. The first law of thermodynamics: energy is conserved. It cannot be created or destroyed, only transformed. The second law of thermodynamics: entropy always increases. Waste heat is mandatory. Einstein's field equations, mass energy curves, space-time. Accelerating mass energy produces gravitational radiation. Together, these three laws form a kind of cosmic auditing system. Every civilization that does significant work leaves a physical record. Not a cultural record, not a biological record. A physical record written in infrared photons and space-time ripples that propagates outward at the speed of light, permanently, forever. This principle appears in other contexts with remarkable consistency. Consider the Earth itself. Our civilization, Kardashev Type 0.73, by current estimates is already detectable from interstellar distances. In 1974, the Arecibo Observatory broadcast the Arecibo message toward the globular cluster Messier 13, 25,000 light-years away. But more significantly, our unintentional electromagnetic leakage radio broadcasts, radar, television signals has been expanding outward at the speed of light since the early 20th century. As of 2024, a sphere of radio frequency information approximately 200 light-years in radius surrounds our solar system, detectable by any civilization with a sufficiently sensitive receiver. We did not choose to announce ourselves. The physics of our energy use did it for us. The same principle governs detection in biology. A living cell produces heat. A metabolically active organism cannot hide its thermodynamic signature from a sensitive enough calorimeter. Even the act of thinking of running electrochemical signals through neural tissue produces measurable heat. The brain generates approximately 20 watts of thermal power. You cannot think without radiating. Scale this to a civilization. The principle is identical. The only variable is magnitude. This is also why the Drake equation, the probabilistic framework developed by astronomer Frank Drake in 1961, to estimate the number of communicating civilizations in the galaxy, has a hidden thermodynamic assumption built into it. Drake's equation asks, How many civilizations exist and are communicating? But the deeper question the equation does not ask is, of those civilizations that exist, how many could physically avoid detection by a sufficiently instrumented observer? The Thermodynamic Visibility Law answers that question. The number is zero, not small. Zero. So now armed with this understanding, when you look up at the night sky and feel the weight of the Fermi paradox, you are not just contemplating an unanswered question. You are reading a thermodynamic audit. The silence of the cosmos is not ambiguous. It is not a data gap. It is not the result of aliens being polite or cautious or philosophically committed to non-interference. The physics of gravity, thermodynamics, and general relativity collectively say, if they were here in sufficient numbers and capability to be setting us, we would have seen the energy signature already. In infrared surveys, in gravitational wave data, in anomalous stellar dimming, in radio frequency excess. Now, when you hear someone describe the zoo hypothesis, the idea that aliens are watching but choosing not to interfere, you understand precisely what physical assumption that hypothesis requires. It requires that a civilization can achieve interstellar travel capability while simultaneously remaining thermodynamically invisible. And you now know that the second law of thermodynamics makes that a physical impossibility. When you read about LIGO detecting gravitational waves, you understand that we have not just opened a new observational window on the universe. We have extended our civilization detection apparatus into a new domain and extended the silence into that domain as well. When you hear about the next generation of infrared space telescopes, the Nancy Grace Roman Space Telescope, or the proposed Large Ultraviolet Optical Infrared Surveyor, you understand that these are not just tools for studying galaxies. They are instruments for conducting the most consequential census in the history of science. And here is what the data actually shows about what that silence might mean. There are three surviving interpretations, scientifically defensible ones consistent with the thermodynamic visibility constraint. First, intelligent life is extraordinarily rare. Perhaps rare enough that we are alone, or nearly alone, in the observable universe. This is the position associated with the rare Earth hypothesis, articulated by paleontologist Peter Ward and astronomer Joe Kirschvink in their 2000 book of the same name. The combination of conditions required for complex life, a large stabilizing moon, a Jupiter-class gravitational shield, a position in the galactic habitable zone. A long-duration stable star may be so improbable that civilizations capable of interstellar travel are separated by distances so vast that their thermodynamic signatures have not yet reached us. Second, intelligent life arises commonly but consistently destroys itself before reaching Kardashev type 2. This is the great filter hypothesis, proposed by economist Robin Hanson in 1998. The filter, the barrier through which no civilization passes, either lies behind us, meaning we have already survived the hardest challenge, or ahead of us, meaning the hardest challenge is still to come. The absence of detections provides no way to distinguish between these, but the thermodynamic argument adds a constraint. Whatever the filter is, it operates reliably across all civilizations in the observable universe across 100,000 galaxies and their combined hundreds of trillions of stars. Third, the universe is younger than it looks, relative to the timescales required. Cosmologist David Kipping at Columbia University has modeled the timeline of abiogenesis, the origin of life, using, say, in statistical inference on the single data point we have, Earth. His 2020 paper in the Proceedings of the National Academy of Sciences suggests that while the rapid origin of life on Earth is consistent with life being common, the development of intelligence may require timescales comparable to the total main sequence lifetime of a star. We may simply be among the first early arrivals in a universe that has not yet produced its density of complex civilizations. All three interpretations are consistent with the thermodynamic silence. None of them require aliens to be hiding. But here is the question that Feynman's framework cannot answer, and it is the one that should keep you thinking long after this video ends. The Thermodynamic Visibility Law tells us that advanced civilizations cannot hide, but it only applies within the observable universe. The 93 billion light-year sphere defined by the distance light has traveled since the Big Bang. What lies beyond that horizon is, by definition, causally disconnected from us. No signal, no gravitational wave, no infrared photon from beyond that boundary can ever reach us. Not because of distance alone, but because the expansion of the universe, driven by dark energy, is accelerating. Galaxies beyond a certain distance are receding from us faster than the speed of light. Their thermodynamic signatures, however loud, are being stretched, redshifted, diluted, and ultimately erased by the expansion of space-time itself. So, here is the unresolved question. If the great filter lies ahead of us, if the reason for the silence is that civilizations consistently destroy themselves before becoming thermodynamically visible, then the most dangerous moment in the history of any civilization may be precisely the transition point we are living through right now. The moment when a species becomes capable of planetary-scale energy use, but has not yet developed the wisdom to manage it. Feynman spent the last years of his life not on particle physics, but on the question of how human beings think, how we build mental models, how we confuse the map for the territory, how we mistake the name of a thing for the understanding of a thing, he said. The first principle is that you must not fool yourself, and you are the easiest person to fool. The zoo hypothesis fools us. It tells us we are watched, protected, significant, without requiring a single piece of physical evidence. It is a story we tell ourselves because the alternative, that the universe is vast, old, and largely empty of minds, that made it is one of the most disorienting ideas a human brain can hold. But here's what the data actually shows. The universe does not owe us significance, and the silence read correctly through the physics of gravity and thermodynamics is not a mystery to be explained away. It is the most important measurement humanity has ever taken. A measurement that says, with the authority of three fundamental physical laws, we may be, in some meaningful sense, alone. And if that is true, if the great filter is behind us, and the long silence of the cosmos is the echo of every civilization that did not make it, then what we do next matters in a way that is difficult to fully comprehend. Not just for us, potentially for the future of intelligence in this corner of the universe. That question, whether the filter is behind us or ahead, is one the next video in this series tackles directly. Using the geological and biological record of Earth's 5 mass extinctions, we can actually construct a probabilistic estimate of where the